Hello, I'm talking to you. This is Goddess of Science Physics, and I'm Mrs. Bolvin. And today, in part 4 of my wave series, we're going to talk about wave speed. How exciting! Okay, let's get going. So the main idea here is that you can calculate speed of a wave by multiplying the wavelength by the frequency. Ooh, I feel like there's a formula coming on. Let's see. So the velocity of a wave depends upon the medium the wave moves through. And you know this because you could imagine, I would think, because if you have a wave moving through like water, which is a fairly, you know, loosey-goosey liquid, the wave's going to move faster than if it moved through something like, oh, I don't know, Jello or a more solid kind of thing. So how fast it goes depends upon what it's moving through. So in a medium, the velocity of the wavelength, which is lambda, I know we're using Greek letters, but that's what they use, and frequency of the wave are all related. So here's our formula. Velocity equals lambda times f. So where v is the wave speed, lambda is the wavelength, you already know that, and f, lowercase f, is the frequency. Okay, so if the wavelength is 1 meter, 1 wavelength per second passes a pole, then the speed of the wave is 1 meter per second. Well, that kind of makes sense. So if you're looking here, if the wavelength is 1 meter, okay, and it goes from here to here in 1 second, that's kind of like velocity equals distance divided by time. It's going a distance of 1 meter in 1 second, so that kind of makes sense. It's just a different way of doing the velocity equals distance divided by time. Instead of time, we're using frequency, so that's a little bit different, but it's kind of the same concept. I apologize for this all coming in at once. So in air, lambda times the frequency is exactly the same for every frequency of sound. So high-pitched notes, when you're listening to a band concert, the high-pitched notes from the piccolo reach your ear at the same time as the very low-pitched notes of the tuba. It isn't that one reaches you before the other, because that would make music sound really, really weird. So it doesn't really matter in air what the frequency is. The lambda times frequency is going to be exactly the same. As long lambdas, long wavelengths have low frequencies, and short wavelengths have high frequencies. So here's a little chart that kind of explains what's going on here. If the wavelength is 2 meters and the frequency is 160, then the wave speed is this. As you decrease the wavelength, notice what happens to the frequency. It increases, but the wave speed is exactly the same. So really important that you realize that in air, sound waves all travel at about 340 meters per second. And if they have a long wavelength, that means the frequency is going to be less. If they have a short wavelength, then the frequency is going to be greater. Okay, thanks for joining me. Have a great day.